Yes, we are recording.
Hi, everyone. Welcome to another excellent Talk Math with your friends. I'm pleased today to introduce Kameryn Williams. They are a postdoc at Manoa, and we would like everyone to know that Kameryn is on the job market this year, looking for teaching positions. So if you have any leads on anything like that, please hit them up and take it away, Kameryn.
Awesome, thank you. And I suppose thank you for saying my talk is excellent before I actually give it. That's certainly showing some faith in me. So I like this topic because, so you'll see when I talk, I'll have a bunch of stuff from like the 1930s I'll talk about. And then I'll end by talking about this universal algorithm due to Hugh Woodin that's from 2011 is when he did it. And then there's been some like recent developments since then. And so it's, it's kind of interesting because it's not using like super, or at least his version of it isn't using super advanced new stuff, but it just kind of hadn't really been noticed that you could do this sort of thing for a few decades. But I think it's a really nice result. So let me kind of start by giving you a bit of history. So David Hilbert had this program, wanted to do some stuff about the foundations of mathematics. And as part of this, he wanted an algorithm that would, given a logical formula, you could determine whether it's true in all structures. And pretty famously, Turing and independently Church showed that there is no such algorithm. Cannot actually do that. Okay, so in a little bit more detail, so if you want to exhibit an algorithm to solve Hilbert's Entscheidungsproblem, then the strategy is straightforward. Just come up with an algorithm and show that it actually does what you claim it does. And, the notion of algorithm, this goes back literally millennia. So like Euclid's algorithm, for example, is well over 2,000 years old. The word algorithm itself comes from the name of, I'm going to mispronounce this, Al-Khwarizmi, a Persian mathematician from like the 800s. And so, this is very clearly an old concept, but on the other hand, showing that you can't have an algorithm is less straightforward. You can't just you can show lots of specific algorithms don't work, but how do you kind of prove this negative? And so really what you want then is you want an abstract notion of algorithms so that you can take this abstract definition and do math with it. So Church, Turing, and then others gave formalizations, which later turned out to be equivalent. And then since then, especially with the rise of computer science, there's been an explosion of equivalent characterizations. So if you take your favorite programming language, unless it's say something like HTML, which isn't powerful enough, then you can use your favorite programming language to give a characterization of algorithm, computability, and all these concepts like that. And so what's nice about speaking in 2020 is computers are so ubiquitous. I'm literally speaking to you over a computer that everyone knows, kind of has a good intuition of what an algorithm is. And so it's not so necessary to see a long formal definition. That's actually probably unhelpful. So I'm going to skip giving a formal definition. Just, think something you can tell your computer to do in a bit of an idealized form, something like unbounded time and memory. Okay. So how specifically did Turing go about doing this? Is he showed that you could reduce this Entscheidungsproblem problem to what he called the halting problem. And so what does the halting problem say? The question is you're given a program, so I'm going to call these things Turing machines because that's kind of the standard. And you want to know, given your program and given your input, is it ever going to halt and produce an answer? So if you've ever done any programming, you know how easy it is to make a program that it loops infinitely. You just mess up your statement of a while loop or something, and then you start running it, it will never stop. And, you'd like to be able to check in advance, is my program ever going to stop, or maybe it will run forever? And so Turing showed famously that, no, this is not possible. There's no Turing machine, no algorithm, if you want to call it that will tell whether a program halts. Okay. And so basically then is his argument I've broken down into two parts. So what I call the hard part is showing that his notion of this abstract machine is sufficiently powerful. So Turing machines are strong enough that they can do computations that use other Turing machines as input or act on them. So in particular, he showed you can have a universal machine that can simulate any Turing machine. It's powerful enough to do that. Once you have that, that's kind of, the hard work, and then the easy part is you do a diagonalization argument with that. Okay. And I want to highlight that there's what you might call other hard part, which maybe is not so surprising now, 90s or just under 90 years later. But, when he did it at the time and before people kind of had these formal notions is, why does his formal concept capture the intuitive notion of computability? And I won't really have time to say this, but there were people at the time, Gödel, for example, due to some technical results, thought that, there might not be a way to have a single formalization that would capture the notion of computability, that any formalization you have, you could kind of diagonalize it against to produce an intuitively computable function that's not actually computable. But Turing actually then found a way kind of around that, and I think his original paper is, kind of a great one to read exactly because of this sort of conceptual analysis that argues that why his notion is a good one.
Really?
Was that a question in the chat?
Oh, sorry, no, talking to my cat. Let me mute myself.
All right, no worries. Okay, so let's talk about the easy part, and the hard part is, I don't know, let's call it homework for you to do on your own time. So we want to show that there's no Turing machine that solves the halting problem. So what do? Is we prove it by contradictions. Suppose H for halting, is a Turing machine which does solve the halting problem. And we're going to use H to build a new Turing machine D for diagonalization. And so what we're going to do is our program D is going to accept another Turing machine P as input. And so what we're going to do is we're going to take that input and we're going to feed it into H with itself. So H is going to look at P with P as input, do some black box computation, and then after some finite amount of time, spit out either yes, it halts, no, it doesn't halt. If yes, then we're going to go into an infinite loop. So that's if it does halt. If it doesn't halt, then D is going to flip that bit and output yes. Okay. And so now let's feed D into itself. So what happens? Well, if D does halt, then H is going to correctly say that. H will say yes. So we'll go through the if no, and then D will output yes. And so if it doesn't halt, then we're saying the output is it's yes, if and only if no. That doesn't work. I'm sorry. I said that backwards. If it does halt, we go through the if yes, and then we get the infinite loop, so it doesn't halt. If it doesn't halt, H will notice this, output no. We'll go through here, it will halt and output yes. So if you input D to itself, it would halt if and only if it doesn't halt. Obviously, that's a contradiction. So our original assumption we could solve the halting problem with the Turing machine has to be false. Okay. So I want to kind of change gears, not really. So I want to talk about another kind of undecidability. This is kind of proof theoretic instead of computability theoretic. And after I talk about this other form, then we'll see how the two kinds of undecidability relate. So again, let's do a little bit of history. So Hilbert, poor guy, had some other things he wanted to solve. One thing he wanted axioms that could decide all questions of natural number arithmetic. So kind of the idea, you want to know, like, is Fermat's last theorem true? You can represent Fermat's last theorem just by quantifying over natural numbers. And you would just have your axioms, and you could just mechanically look for proofs from that. And eventually it would say yes or no as you search through the proofs. You would be able to decide any question just by looking for proofs from those axioms. And Gödel then proved that no, you can't do that. And so let's talk a little bit about this sort of incompleteness of arithmetic and the undecidability there. Okay. So what specifically did Gödel prove? So let me take for my axioms of arithmetic what's called piano arithmetic. It's so called because Dedekind was the first really to have this idea. And so basically what does piano arithmetic say is it says, well, the natural numbers are a discretely ordered semi-ring. So like a ring, but you don't have additive inverses. And then you have axioms for induction. And I'll say more on a later slide about what exactly that induction axioms are saying. Okay, and so Gödel has two incompleteness theorems. I'm giving forms of both of them. So a form of the first incompleteness theorem says that if you take an extension of PA, then as long as its axioms are computable, then it can't be complete. There has to be some statement. It doesn't say give a yes or no answer to. It just doesn't prove one way or the other. Maybe kind of an example in a different way is not related to arithmetic, but incompleteness, is take the axioms for groups, take the statement, the relation is commutative. This statement is undecidable from the axioms of group theory, because there's abelian groups and there's not abelian groups. So you can't prove it one way or the other. And so this is showing that if you want to, not for groups, which of course no one expects the axioms of groups to be complete, but if you want to do this for like natural number arithmetic, then there's no way to do it. And then the second one is he gives a specific example of something that, say, PA can't prove. So PA can neither prove nor disprove the consistency of piano arithmetic. So if you just want something simple, like you want to prove that, oh, I'm never going to get a contradiction from these axioms, then you're going to need more than PA to prove this. Okay, and then much like with Turing, is you can kind of split the work into a hard part and an easy part. So the hard part is actually showing that you can do all the work to talk about this. So this is this arithmetization of syntax is what people call it. So Gödel showed that you can code logical formulae as natural numbers. And so statements like PA is consistent can be coded as a statement about natural numbers. And then once you have all that hard work done and you know that you can talk about logical formulae in arithmetic, then you do a diagonalization argument similar to the one for the halting problem. And I want to highlight this computably axiomatizable restriction. You might ask, why do you need this? And just kind of, there's a silly kind of trivial counterexample. If you look at what we call true arithmetic, so this is just everything that's true in the natural numbers. This is extending PA, because PA is true in the natural numbers. The natural numbers are a discretely ordered semi-ring and have induction. But this is complete, just kind of trivially, because anything you want to prove from true arithmetic, you have a one-line proof. Either phi is true, so you have just put down phi, or phi is false, you put down dot phi. It's just an axiom, whether it's true or false. And so you get kind of this silly counterexample, so you do need some sort of restriction on what you look at, and computably axiomatizable is the one that ends up working out. And I guess as an aside, if you know a little bit more computability theory, then the low basis theorem gives you computationally less complex things than true arithmetic. Okay, so I want to say a little bit about arithmetization. I won't give like the very formal statement because that's not a nice thing to do at a friendly talk. And so the way to think of it, the important point is what's known as Gödel's beta lemma, and he shows that you can code an arbitrary finite sequence in a single number. So you can have a number, then you can write down a formula that says, you know, what's the length of the sequence it codes, what's the I thing on it, what's the first thing, the second, the third, and so forth. And so then you can think of natural numbers as coding sequences. So maybe kind of a simple way to kind of pump your intuition is think about writing the way we do in computers. We represent everything in binary, zeros and ones. So what's a string of zeros and ones? That's a really big number. So your computer might have like an array of numbers. That's just a really long sequence of zeros and ones. That's just a number. And so it's a similar sort of idea, but it's, you know, you want to show that it can work just with what you're given in piano arithmetic, not necessarily all the tools that you might have in a modern computer. And so hopefully it's a, you know, with computers being so ubiquitous, this is a very believable statement that numbers can code a lot of information. And so kind of the important point also, this will come up later, is his lemma here is actually provable just within piano arithmetic. So he checks that as well. And so once you can code finite sequences, you can code any finite mathematical object in arithmetic. And so let's take semi-rings for an example. The natural numbers are a semi-ring, so let's look at semi-rings. So what's a finite semi-ring? Well, you want to have a set R and then a plus and times on R that satisfies certain axioms. So you should have like associativity for both of them. They should both be commutative. They should have the appropriate distributive law, etc. And so how do you represent this in sequences? Well, R is a finite set, so just list its elements in a sequence. And since we really only care about things up to isomorphism, its elements might as well just be natural numbers. So like I did an example here, I called it 1, A, B, and 0. Just pick 4 natural numbers to be these 4 elements to represent them. And then how do you represent plus and times? Well, these are just finite multiplication tables, so you can just have a sequence that just lists off what happens. So if your 2 inputs are, say, A plus A, the output is going to be A. If your 2 inputs are B times A, the output is going to be 0. And so then you can just write a single formula in arithmetic, which says the natural number n codes a finite semi-ring. It's a sequence with 3 elements. The first one's the set, then you have the plus, the times, and they satisfy all these things. Okay. More relevant to what I'm talking about is objects like Turing machines or logical formulae can also be coded in arithmetic. Why? Because they're finite mathematical objects. You can just represent them by talking about enough finite sequences of finite sequences and so on. And so once you get that, statements like saying that PA doesn't prove 0 equals 1, this is how we like to say that PA is consistent, or saying that such and such Turing machine halts, these are all just statements about natural numbers now. There's absolutely no need to talk about anything but natural numbers. And all of this, you can then ask questions like, does PA prove that this Turing machine halt? Does PA prove that PA does not prove z equals 1? These are just statements about natural numbers. Okay, so here is maybe a taste of how you do this formalization. So I took this with permission from Vika Gitman's lecture notes for class she taught. So if you want to try to just express what does it mean to be an axiom of piano or a numbered coda, an axiom of piano arithmetic, then you want to do something like this, and things like form or length or free or sub, these are all abbreviations for themselves formulae of arithmetic. So hopefully it's clear that this is not so like easy to, it's not, easy is the wrong word, it's verbose, I'll say. There's a lot of details to check. And so that's why I say it's the hard work. I think in the 21st century, it's very believable, but actually showing it is where the hard part is. And on the other hand, the easy part is self-reference. So after that last slide, I think you need a break. So please enjoy this meme at the expense of Douglas Hofstadter. Okay, so why am I making fun of Douglas Hofstadter? It's maybe not fair to him, but a lot of people see stuff like the incompleteness theorems and they see the self-reference as the hard part. Whereas, like I said, I think the hard part is the arithmetization and the self-reference is the easier part. But of course, if you want to do diagonalization, you have to flip it. So you have to put a not in there. Okay, so let's talk about the self-reference you need for these. So Gödel has the fixed point lemma, and it basically says that you can have a sort of self-reference for logical formulae. So you can have a sentence that's equivalent to saying some property phi holds with that sentence. And so once you have this, then this is really what you need to prove the first incompleteness theorem, or I should say a form of the first incompleteness theorem. So take a sentence sigma by the fixed point lemma. We can find a sentence sigma, which is provably equivalent to the statement sigma is not provable. And so now let's ask, is sigma decidable from PA? Does PA prove sigma or not sigma? Well, if PA proves sigma, then because sigma is equivalent to saying sigma is not provable, then PA proves that sigma is not provable. But then we can conclude that PA does not prove sigma, contradiction. On the other hand, if PA does prove not sigma, well, not sigma is equivalent to saying that sigma is provable. So then we would prove that sigma is provable, but then we would prove both not sigma and sigma, but piano arithmetic's consistent, contradiction. Okay, I guess spoiler, not spoilers, like confession, you do need an additional lemma for these two wences, and we'll come back to that later. Okay, so it's, you know, maybe the incompleteness terms are hard to prove, but if you hand wave over the hard parts, then the proof fits on one slide. Okay. Let me also mention here, because I will need this later, is you can also have self-reference for computability theoretically via like Turing machines. So the Kleene recursion theorem is kind of the big one here. There's other ones we won't talk about. And basically in formally, it says that Turing machines can refer to themselves, their own source code. So an application that I think is fun, and this is a common exercise to assign to like logic students when they learn about the Kleene recursion theorem, is programming languages have what's called a quine, which is a program that outputs its own source code. So I mean, you can cheat by just like reading it off the hard drive. This is, you're not supposed to cheat. You're just supposed to have a program that outputs its own source code. So I put one in Common Lisp because I think Lisp is a good language. If you like another language, you can come up with quine in your language. And how do you do this is just basically implement the proof of the Kleene recursion theorem in your programming language. And you do that, and then you can have it output. You'll write a program that outputs a quine. Okay, so I want to now tie together these two kinds of undecidability. This proof theoretic undecidability Gödel looked at, and the computability theoretic undecidability that Turing looked at. So the incompleteness theorems, you can recast as saying that whether certain Turing machines halt is undecidable. So piano arithmetic, or whatever axioms you like, can't prove that one way or the other. And it's not so deep. So let's look at how you might do it kind of in the stupidest way possible. So take a Turing machine program, call it P, And what we're going to do is we're going to look through all the proofs from the axioms of piano arithmetic. So how do we do that? Well, we know what the axioms of piano arithmetic are. It's computably axiomatizable. So let's just look at all length 1 proofs from the first one axiom. Okay. And then after we look at those, then we're going to look at all length 2 proofs from the first 2 axioms, then all length 3 proofs from the first 3, then all length 4 from the first 4, and so on. So at stage n, we're looking at all length n proofs from the first n axioms. And so if at any point we ever see a proof that ends with 0 equals 1, then that means we just showed that PA is inconsistent, because the only way we're going to prove 0 equals 1 is if it's inconsistent. So if at any point we see this, we're going to halt and output yes. And so basically what this Turing machine is, this Turing machine halts if and only if PA is inconsistent. And so whether or not P halts is going to be, PA can't prove one way or the other, because if it halts, then that would be get a proof of consistency, and PA is not strong enough to do that by the second incompleteness theorem. Okay, so this is, like I said, this is a very kind of stupid brute force approach. It's going to take a very long time for this program to do anything. It's going to be a very long program. All the stuff I showed on a few slides back about arithmetization, now you want to implement that in your Turing machine. So you have all this complicated stuff to do. And I didn't calculate the size of this, but it's pretty massive. You could do a lot better. So recently, I think 2, maybe 3 years back, Adam Yedida and Scott Aronson of MIT did even better. So they constructed a pretty small Turing machine, size under 8,000, so that whether or not this Turing machine halts is independent of ZFC. ZFC is the axioms for set theory, much, much stronger than PA, incredibly much stronger than PA, but it's not strong enough to show that this specific Turing machine halts. But on the other hand, if you extend ZFC with even stronger axioms, then you can prove it halts. And of course, these stronger axioms, we still have a computably axiomatizable theory, so we're going to have other Turing machines that it can't prove halts. We're always going to have this Turing machine we can't prove one way or the other whether or not it halts, just because of this incompleteness phenomenon. So it's not just that you can't computably decide whether a Turing machine halts. You can take strong axioms that tell you about a lot of uncomputable objects, infinite objects, and even then there's going to be Turing machines you can't decide whether or not they halt. It's just baked into the foundations of mathematics. Okay. So I want to maybe move to talking about what I think is an easier way to kind of view what's going on. And so this is basically, rather than talking about proofs, consistency, etc., I just want to talk about mathematical structures. And so the bridge between talking about proofs and talking about structures is Gödel's completeness theorem. So he proved his completeness theorem. A few years later, proved his incompleteness theorem. This is as bad as when Tarski first defined truth and then later proved truth is undefinable. It's maybe not a fantastic naming convention. But what does the completeness theorem say is it relates proofs and mathematical structures. So one way of formulating it is saying that you have a set of axioms T, maybe T is piano arithmetic, maybe it's Z of C. And so this set of axioms is consistent. You don't prove a contradiction if and only if you can find some structure satisfying those axioms. And then another way of doing it is about entailment. So something is true in every structure satisfying T. This is semantic entailment if and only if it's provable from T. And so if you then want to take the incompleteness theorems, for example, say that consistency of PA is independent of PA. And so that means that PA plus con PA is consistent. PA plus not con PA is also consistent. So we've got 2 different incompatible sets of axioms for arithmetic. And by the completeness theorem, there's going to be structures satisfying each of those. That means we're going to have non-isomorphic structures which both satisfy the basic axioms of arithmetic. And so what could these non-isomorphic structures even possibly look like? Okay, so let's talk about non-standard models of arithmetic. Like I said, I think it's easier to think kind of semantically about structures than think about proofs. If it's the other way around for you, then that's also fine, but I think I still want to talk about this. Okay, so what is a model of arithmetic? So it's got to satisfy the axioms of PA. So it's got to be a discretely ordered semi-ring. That was one of the axioms. And we need to satisfy the induction axioms. What do the induction axioms say? They tell you that definable subsets are inductive. So inductive just means you satisfy the if-then definition for induction. And definable is just saying that you can express whether or not you're in the set by just quantifying over the elements of M and using the operations in order. So you can't quantify over subsets, just elements. So one way of thinking about where this comes from then is that the natural numbers, every set is inductive, whether or not it's definable. And we know that the natural numbers are the only object that satisfy this. If every set is inductive in this sense, then you have to be isomorphic to the natural numbers. So to have a non-standard model, you can't have every set be inductive. You have to restrict that somehow. And so the restriction is we restrict it to these things that are kind of internally viewable to the structure. Okay, and so that's kind of the basic definition then, and let's maybe look at some properties of these and see how we use these. So the first thing is, let's notice that the 0 of M, that is the additive identity, is the least element of M. And why is it? Is because if you look at the set of things in M that are at least as big as 0, that satisfies the induction hypothesis. 0 is in this set, and it's closed under adding 1. So it has to be all of M. And that means that 0 is the smallest thing in M. And now that you know 0 is the least element, there's a next element 1, kind of by similar reasoning. There's the next element 2, we'll call it. There's the next element 3, and you can keep going. And so you're always going to be able to just, once you have a thing, there's going to be a next one. So if you map 0 to the least element, you'll map 1, then 2, then 3, then 4, and so on. And at the end of the day, what you get is that our non-standard model M has the natural numbers as this initial segment. So I say embeds, but you might as well just identify it up to isomorphism. And so what that means then is that what we have looks like the natural numbers with this weird extra stuff put on the end. Okay, so maybe let's look at this extra stuff on the end, the so-called non-standard part. So because the natural numbers is an initial segment, if you take something not in the natural numbers in M, it's got to be bigger than everything in the natural numbers. Okay, that's not saying much. But maybe can we say a little bit more? So one thing we can say is just like you can add 1, add 2, add 3, and so on to 0, you can do the same thing to E. You can look at E plus 1, E plus 2, E plus 3, and so on. And these all exist, and they're going to have nothing in between because of this discrete ordering on the semi-ring. If you take E and E plus 1, there's nothing in between. That's part of what it means to be a discrete order. Okay, and so that gives you E plus all the natural numbers. But you can also subtract natural numbers or add negative integers if you prefer to think of it that way. So why can you subtract? And you can do this by these induction axioms. So look at the set that contains both 0 and everything that has a predecessor. So you can subtract 1. Then this satisfies the induction hypothesis. It contains 0 and it's closed under plus. Because if A has a predecessor, then A plus 1 is a predecessor. That's just true. A plus 1 always has a predecessor, namely A. And so this has to be all of M. So all of M either is 0 or something where you can subtract 1. So from E, you can subtract 1, subtract 2, subtract 3, subtract 4, and so on. And you get this little Z block centered on E. And so E plus or minus this Z block, there's kind of nothing in between these elements. It just looks like a copy of Z laid out here. Okay, but let's look now at 2 times E. We can multiply by 2 because 2 is an element of our domain and we have multiplication. And so 2E is of course the same as E plus E. And that's going to be bigger than E plus N for all natural numbers N because E is bigger than N. And so this means that everything in this Z block is smaller than 2 times E. And similarly, everything in this Z block will be bigger than everything in this Z block. So we have a Z block, and then we have a separate Z block that's just completely larger than it. So you have this like copy of Z, and then off to the side, you have this other farther even out copy of Z. Okay, and then you can do the same thing, except instead of multiplying by 2, you divide by 2. And you have to take the floor because we're talking about basically natural numbers. And again here, it's going to be a separate Z block. It's going to be outside this Z block, because if you multiply E halves times 2, that's going to be, or E halves plus N is smaller than E for all natural numbers N, because of E halves is bigger than N for all N. And so we get another Z block here, and then we can kind of keep filling in. So if we go halfway between E and 2E, we get another Z block. If we go halfway between E and E halves, we get another Z block. We could get one farther on the right by multiplying this by 2. And so what we end up getting is we get a dense linear order of Z blocks. So we have the natural numbers at the beginning, and then all these z blocks, but they're arranged like a dense linear order. So between any two z blocks, you can always find another z block in the middle. So the z blocks themselves are kind of not discretely laid out. Okay.
So is the
Yes.
density like Q? Sort of how we're
Excellent
thinking?
question. You're anticipating my next slide. All right, so just some facts about these, and I'll get to Brian's question at the third bullet point. So just historically, Thorolf Skolem was the first to construct a non-standard model of arithmetic. There's lots and lots of non-isomorphic models of any infinite cardinality. In particular, if you just want to look at countable ones, there's as many as there can be, continuum many. And maybe let's say a little about the order type. So if we look at these countable models, then we know exactly what the order type is. It looks like n followed by q many copies of z. And this is because Q is the unique up to isomorphism, countable dense linear order without endpoints. So if you haven't seen a proof of this before, it's a really neat fact. It's, you know, if you want to ignore the rest of my talk to think about how to prove it, that's a good use of your time. And so in particular then, all of these countable guys are going to be order isomorphic. So their plus and times could be very different, but their less than relation always looks like n plus q many copies of z. And then just to kind of give a taste of the area here, let me mention this open question by Harvey Friedman. This is from the late 80s, early 90s, I want to say. So n, the natural numbers, has the property that if something's order isomorphic to it, has the same order type, then it's actually fully isomorphic. It has the same plus and times. Does any other model of arithmetic have this property? So can you have some non-standard model so that order isomorphism guarantees full isomorphism? So by this bullet point number 4, that can't happen if it's countable. It would have to be uncountable. And we know basically very little about this question. So it's Shalahard, for example. Zahar and Shalah thought about this and made partial work and couldn't come close to solving it. So it's a quite difficult question that's maybe kind of easy to state. Okay. And then another fact I like is Tenenbaum's theorem. So kind of to give you a grasp on these non-standard models. So if you do have a non-standard model, maybe you know what its less than looks like, but its plus or times can never be a computable function. So these are inherently uncomputable objects.
Cameron,
Okay.
we've been talking in the chat. Why are you allowed to divide E by 2? Joel sort of says you can prove every other thing is a multiple of 2, but
exactly. Yeah. So think of how you like prove that every other number is even. You want to use induction to do it. This is like a good exercise for your infinite proofs class. And so that argument you can just internalize to PA, because PA says you can do this kind of induction. And so that's why you can divide by 2, taking the floor. And more generally, so it's just basically the Euclidean division algorithm. You prove that works by induction. And so that means it's going to work in any non-standard model because the proof just goes through in piano arithmetic. Yes, great question. Yeah, so maybe let me just say in response to that, yeah, having induction is incredibly powerful for what it allows you to do. Because if you just take an arbitrary discretely ordered semi-ring, you can't do this in general. So for example, if you just take the natural numbers and add infinity on and do the obvious plus and times for that, that's a discretely ordered semi-ring. Obviously, or maybe that's a bad example because you can divide infinity by 2 by just getting infinity. Okay, but you can have badly behaved discretely ordered semi-rings, and induction imposes a lot of structure. Okay, so let's maybe talk about what Turing machines look like in these non-standard models of arithmetic. So let's take kind of a twist on this Turing machine I talked about earlier. We're just going to enumerate all the theorems of piano arithmetic. So again, we just look at the length 1 proofs, the length 2, length 3, length 4 out, and so on. And we're just going to eventually print off everything that piano arithmetic proves. Okay, so like I said earlier with arithmetization, we can think of P as being some natural number. And we can think of a theorem like 2 + 2 = 4. That's a good theorem of arithmetic. That's just a natural number. The statement 2 + 2 = 4 is some natural number much bigger than 4. Okay, and so what does it mean that P outputs this? Well, it means that we have basically a log of the computation. So you could just basically think it says if you run P, then the first step looks like this, the second step looks like this, the third looks like this. After finitely many steps, you have the output. And so what is this computation log? It's just a sequence. It's just a finite sequence showing what happened, satisfying certain properties you can write down. And so S is also a natural number. Everything finite we can think of as a natural number. And indeed, we don't have to look beyond the natural numbers to find this computation log. This thing really does output this, and so we're really going to find this in the natural numbers. Okay, so P outputting 2 + 2 = 4 is witnessed by some natural number S. Okay, so if we run P in the natural numbers, we're never going to output 0 = 1. That's another number, and it's never going to be output because it's not a theorem of arithmetic. On the other hand, though, our non-standard model M might think that PA is inconsistent. If it thinks PA is inconsistent, then it's got to think that we output 0 = 1, because eventually we're going to prove phi, then we're going to prove not phi. We're going to put those proofs together. We're going to use phi and not phi implies 0 = 1. That's just logically valid. And then we're going to, by modus ponens, conclude 0 = 1 at the conclusion of our theorem. So if M is a non-standard model, which thinks PA is inconsistent, then we will output 0 = 1. And what does it mean to output it? It means there's a computation log showing that you did these steps. So this computation log, this number T, that shows that we output 0 = 1, has to be non-standard. Because if it was in the standard part, then running it in N, we would have eventually seen that computation log, and in the natural numbers, we would have output this. And so in other words, what happened is, how did we get our program P to output the theorem 0 = 1? Is we ran P for a very, very long number of steps. We ran it, it kept running through all the real natural numbers, it runs into the non-standard realm, and eventually it finally, after non-standardly many steps, sees a proof that 0 = 1. And in fact, you can do a bit better than this. You can prove that in order to do this, the program, your proof, has to use a non-standard instance of induction. So it's using a kind of fake or false axiom in order to prove this. Okay. And so what's the point is, by moving to this larger world, we changed what P output. So one way of thinking about this undecidability, this incompleteness then, is the behavior of Turing machines can vary based upon where you run them. If you run this Turing machine in the natural numbers, it never outputs 0 = 1. If you run it in this non-standard guy, it eventually outputs 0 = 1. Okay, so let me kind of summarize some of what we saw here. So statements of the form, this Turing machine outputs this thing for some input, this sort of statement is upward absolute. Because if we go to a larger model, we still have the computation log that witnesses this. On the other hand, saying that we don't output something, saying we don't output 0 = 1, this is not upward absolute. We can change its truth by moving to a larger model. It is downward absolute, though. If it was true, and then we cut off to a shorter thing, it's going to stay true. If you don't see a computation log here, looking at a smaller domain, you won't see a computation log. Okay. And so by what we saw in the last slide, plus the completeness theorem, if you have a true statement like P outputs N, then it's going to be true in every model of arithmetic. But if it's true in every model of arithmetic, it's a theorem of PA. So any true statement like this, PA proves. And so this is the extra step I skipped over in the proof of the first incompleteness theorem. Is a true state, if a statement like PA proves that sigma is not provable, if it's true, then it has to be provable. And on the other hand, these statements, this Turing machine does not output something, these are the sort of things the first and second incompleteness theorems are about. So for these first guys, you have completeness, but once you look at these second guys, you immediately get the incompleteness phenomenon. So it's a very precise calibration of where that window is. Okay, and so now I want to get to the rest of the words in the title. So what we've seen is that Turing machines can have undecidable behavior. So proof theoretically, it might be independently of your axioms how it behaves. Model theoretically, depending upon which model you run it in, you're going to get very different behavior. You run it here, you get one output. You run it here, this thing's not output. And so Hugh Woodin has, I think, a very striking case of this sort of undecidability, where your program P can output anything whatsoever. And so that's what I want to talk about for the remaining 5 minutes or so I have. Okay. So specifically, what did Woodin do? Is he constructed a Turing machine that outputs a finite sequence. So it's going to have finitely many things it outputs. And okay, that's not so hard. The next thing it does is if you run it inside n, it's never going to produce any output. So it enumerates the empty sequence. That's not too hard to arrange. Just have a program that gets into an infinite loop. It's never going to produce an output. And so the real meat is this property number 3. So if you take anything you might want it to output, any finite sequence, then you can find some non-standard model so that you enumerate exactly that sequence by running P in that model. And so Woodin did this as part of like a philosophy paper about a possible subtlety distinguishing determinism from non-determinism. Is it deterministic what this Turing machine outputs? Well, it kind of depends on the underlying laws of the universe, meaning like what model you run it in. Okay. So basically, this Turing machine is universal because you can make it output whatever you want by just running it in the right universe. Okay. And it's, I think, not so terribly difficult to see why exactly this works. So what is our Turing machine going to do? Is again, we're going to look through the proofs of piano arithmetic, and we're going to look at theorems that piano arithmetic proves. And we're looking for a theorem of a particular form. We're looking for a theorem that says this Turing machine P does not enumerate the sequence S, where S is some sequence. So maybe we'll keep running P, and eventually we see a theorem that says P does not enumerate the sequence 1, 2, 4, 8. And if we ever see something like that, the moment we see it, we output that sequence and stop. Okay, so there's a bit of self-reference here. This program P is referring to itself. We're allowed to do that by the cleaning recursion theorem. And so the way kind of I think of this is it reminds me of my cat. The way to get my cat to do something is to tell him he's not allowed to do it. So what does this Turing machine do is it's looking for a rule saying it's not supposed to do something. And once it sees that rule, it says, well, you know, don't tell me what to do. I'm going to do it anyways. So if P ever sees this, it's going to output. If P ever sees kind of the rule, it doesn't output S, it's going to say, no, I'm going to output S anyways. Okay. So let's see this property 2. So if you run this P in the natural numbers, you're going to output the empty sequence. Okay, so otherwise, then you output some non-empty sequence S. Okay, but then we have a true statement about what P outputs. This is a, like we saw, this is one of these true statements. So by this previous slide, this is actually provable. But what does it mean to run P? Well, P output S if it found a proof that P does not output S. And so this means that we also get that piano arithmetic proves that P does not output S. So PA proves P outputs S. PA proves P does not output S. That means it's inconsistent, but we know it's not because the natural numbers satisfy PA. So why does this I'm not going to do what you tell me thing not give us a contradiction? Well, because this P just will never output anything. Okay. And so we want to check the extension property. So we want to show that given any sequence of natural numbers S, we can find a non-standard model in which P outputs S. Okay. So claim is that if we take the axioms of arithmetic and we add the statement P outputs S, that this is consistent. There's no contradiction. And this is really what we just saw, because if this were inconsistent, this would be inconsistent because PA proves that this is false. PA proves P does not output S. But if PA proves it doesn't output S, then what P would eventually see that theorem, and then it would output S and the natural numbers. But we just saw that is not the case. Okay, so this thing is consistent. So by the completeness theorem, there's a model that satisfies this statement. And that's all we needed. Okay, so I think I'm almost out of time. So let me just say there's a more general form of this where instead of starting at the natural numbers, you can start at any non-standard model where the sequence is S, and then you can extend to a further non-standard one in which the sequence is S star if you have any extension. So it's not just like a one-step thing, it's a 2, then 3, then 4, and so on step thing. Okay, I go for 45 minutes, correct, Brian?
We have the hour, so you can definitely wrap up. And then we like to leave time for questions, but
okay. I also have to teach after this, so I don't want to
okay,
go
great.
over. All right, okay, so what's the proof idea for this is you do the same thing, but you kind of internalize the argument. And so you need to check some technical lemma to show that you can arithmetize the argument. But basically, you use this extra machinery, and then you just do the same proof. Okay, aside, can you do this in set theory? There's two ways of doing it in set theory based on two different things. So one, Hamkins and Woodin teamed up to do it for where you add things on top. And then there's another sort of extension that Hamkins and I proved it for. I'm not going to say anything about those. Okay, maybe let me just end by putting this slide up, and I'll leave it up for questions at this point.
Please join me in thanking Kameryn. Yeah, I think most of our questions got asked either out loud or engaged in the chat. But would anyone
yeah,
like
I see there's 50 chats I haven't looked at.
Yeah. Yeah, go for it, Joshua.
I don't know if this is I don't know if there's any question here, but I'm just astounded that I sort of think of computability as one of the few areas of discrete math which is grounded in the real world. And you've just sort of blown my mind by showing that it can be done in systems that have nothing to do with the real world that I can see.
I mean, I think this is maybe what you would expect because, you know, one thing that we like about these certain mathematical things, you know, something like, for example, let me use set theory here. It's maybe easier to say. You can code all kinds of things with sets. So, you know, any sort of math you want to do, you can somehow represent it with sets. And so anything you can do in the real world, if you can kind of make it sufficiently precise that you can mathematize it, then you can talk about it in these formal mathematical statements. So it's just that, you know, math is strong enough to talk about the real world. And so things that are strong enough to talk about lots of mathematical objects will then be able to talk about things like computers.
Yeah, okay, yeah.
Flip the other way around, it sort of says, like, you think you're just describing something simple, but inherently the demons got in, and it's like the complexity was always there. Great. I think Kameryn has to run. Any last question?
One question. So how would we, is there any way we could tell fundamentally that we're actually not living in some sense in a non-standard universe? Like say 12. 12 seems like a perfectly fine number to us, but maybe that's just because like we're really non-standard, and when I start counting to 12, I don't realize I've actually gone through like not into non-standard integers. Is that meaningful?
So, I mean, this is getting into more philosophy stuff, which I think is great, but also I'm one, not sure how qualified I am to talk about it, and two, I think it takes a long time. So let me just say that this sort of view is something that has received serious attention, e.g. Joel Hamkins in the, I think he's still here, has talked about this and argued that the answer is no, we can't tell we're not in some non-standard world.
All of these models have the same finite. If the universe is finite, then all of these models have the same finite initial segment, right?
Right, but I mean, how,
or if the universe is even countable.
But maybe we live in some ill-founded like model of set theory, and so what we think is the real natural numbers is just actually some non-standard thing. And we can see that there's other things that we know are non-standard, but maybe some bigger, better universes that are natural numbers are non-standard. How do we rule out that possibility?
So just so that Kameryn can run, we have two little things. One is just a brief announcement of next week, the mathematics of Sudoku. Joshua, do you want to take 30 seconds to give a foreshadow?
Sure. Can you hear me okay?
Yes.
Yeah. So yeah, just this is kind of a survey of some of the. Turns out, you know, there's some interesting questions about Sudoku that you might not expect. It's obviously like recreational math topic, but it turns out there's some serious questions there, and so yeah, I was just going to sort of blow through some different interesting questions about Sudoku and ways of viewing those questions.
Great. And then the second one is, please join me in thanking Kameryn. We can stay for a little while, so Kameryn might have to run, but if the rest of you want to stay and chat, we can leave it running for a few more minutes. So.
All right, I have a few more minutes because I'm literally just going to teach by opening up a new Zoom chat.
Okay,
So
great.
Immediately, but thank you for
Joel, did you have something you wanted to say?
I have a question about Friedman's theorem. So do you know, are there any...
Friedman's question?
I mean, Friedman's question, yeah, about whether, is there any other model of PA such that the order type determines the isomorphism type, right? That's the question?
Yes. And
so is there anything known about the cardinality of, for example, is it known there couldn't be one of size omega 1 or something like that? Obviously there can't be a countable one because they're all...
Obviously it can't be countable. I once saw Alf Dulles give some talks about Shalah's paper, but that was like 3-4 years ago and I don't remember it so well.
Is it known there can't be an omega 1 like one? Or?
I think omega 1 like is known that it can't be. But this is stuff I haven't looked at in years and don't remember offhand.
Okay.
Great, and looks like Benjamin had a question, but you answered in the chat. About the law of excluded middle. Cool. Any more questions before we run? All right, thank you. This is lovely.
All right, thank you for coming.
Yes. And remember, Kameryn's on the job market.